Welcome, good evening. It's March 26th, and we're in Pierce 116, and we're here for the D4 Exam 2 for the Spring 2018 semester. So I want to thank, as always, our SITTV colleagues, and tonight it was Jesse and our cameraman, and all-around good person is Sean, our colleague who's taking care of everything. So to Matt, Jesse, and Sean, and everyone else behind the scenes, thank you, SITTV, for recording this. All right. What I want to do tonight is make this worthwhile. So I thought we'd go over an exam that's already posted on the course website. Let's go over the most recent exam, which is the Fall 2017 Exam 2. So we'll just dive right into it, and I encourage questions and comments and feedback here as we go through this. So, problem 1 is one of these multi-part problems, and I hope you don't hate me for it. I didn't think any one of these individual parts was big enough to be assigned its own problem, so I just kept writing down like these little individual problems, and you'll see there's a lot of them. So, but that's okay. You know how we begin a long journey? One step at a time. So we'll start off. List the 2 mobile software platforms that are dominant. Apple's iOS and Google's Android. Very good. Excellent. All right. By the way, this exam and its solutions are posted. So the 2 dominant software platforms are Google's Android and Apple's iOS. Now, just to get warmed up, convert the decimal number 743 to binary. How do I do that? How do I? Kristen knows. Caroline knows. You know? Justine knows. I know you all know this. So we have to divide by 2 and keep track of the remainders. So instead of writing all this down, we have the solutions. So let me just pop over to the solution file. And there it is. All right. So we take 743 and we divide it by 2. And that gives us 371, but a remainder of 1. So what we do, my colleagues, is we write down the number, divide it by 2, and we got 371, but the remainder is 1. And we put the remainder here. And what we do is we just keep going. It's so much fun, we don't know when to stop. We just keep going. It's 371 divided by 2, remainder 1, 185. 185 divided by 2 is 92, remainder 1. And we just keep going and going and going. Now, when do I stop? Well, down here I have 5 divided by 2. That's 2 with remainder 1. 2 divided by 2. It's 1 with remainder 0. 1 divided by 2 is 0. That's when I stop. Remainder 1. Now, the only mistake I think you'll make is you might read it down. You got to read it from the bottom up. So notice it's 1011. Ah, 1011. And I had so much fun with this, and I had so much time in my life. I don't have a life. I said, I can double check this. So you don't have to do this for sure. And I said, why not? What else was I doing? So how you double check it is you say on the, starting with the right-hand side, that's 1 times 0 to the, 1 times 2 to the 0. Beg your pardon. 1 times 2 to the 0. The next one is 1 times 2 to the 1. 1 times 2 squared, and so on and so on. And I checked myself, and I got the same answer. Okay. So we just have to divide things out. And while we keep going till we get down to 0, and we're all set. Okay. All right. All right, how we doing? Sarita, I'm thinking of you out there because I see Awa. Awa has an empty seat here, so I kind of virtualize that you are here. Okay, good. Anything else? All right. What's question number 3? In our lectures, we discussed the concept of aliasing. Why does aliasing occur? Why? Ryan from Long Island.
When the sample is, when it's an undersample.
Right. When we don't sample fast enough. Perfect, right? So how do I say that in the fancy answer key? But Ryan, you would have gotten full credit. Okay? Aliasing occurs when the signal is not sampled high enough. Now, Ryan, this was not part of the question, but can I ask you a bonus question? How do I know, like, what is the right sampling? Double the highest frequency in the signal. Exactly. So double the highest frequency in the signal. So aliasing occurs when the signal is not sampled at the required minimum sampling rate or higher. Now, next question. Ryan's already answered it. How can aliasing be prevented? The key concept is we need to sample at least twice the highest frequency. And that's what I have. So we want to sample at least 2 times the highest frequency. That avoids aliasing. How are we doing so far? I like these little questions. Justine's writing them all down here. All right, we're doing good. Now, I move on to part D as in David. You're given a function that is a square wave. Okay. This function of time is periodic and has the frequency of 100 cycles per second. At what frequency or frequencies would you expect the signal energy to be located? Oh, I love this question. What do you think? What's the answer? In fact, how about this? How about as a warm-up question? We have a warm-up question. Suppose you had a sine wave, and the sine wave had a frequency of 100 hertz. Where would the energy be located? See, the question is so easy, you think I'm tricking you. The energy would be located at 100 hertz. All right? So now you have a square wave at 100 hertz. Is all the energy located at 100 hertz? I see very thoughtful, even the home audience, I see very thoughtful looks in people's faces. I think if I now have a square wave, okay, and the square wave has 100 cycles a second, I say, wait a minute, I know an old friend, Fourier. Fourier said we can write this as a sum of sines and cosines. And where is the energy for a sine or a cosine? At the frequency of the sine or the cosine. Now, what else do I remember about the Fourier series? I remember using the musical analogy in class. I'm sure the home audience remembers it. We have the fundamental, which is the first harmonic. What's the next term? The second harmonic. The next term is the third harmonic. So if I have a periodic signal at 100 cycles per second, I would expect that there would be energy at the first harmonic. Now, where would be the next place I would find the energy? Second harmonic. Now, it might be 0, but the next place where there could be energy is the second harmonic. The next place where there could be energy, the third harmonic. So what we have is, I would expect to see energy at 100 cycles per second and multiples of 100 cycles per second. Now, I'm not guaranteed, because we had an example in a class that did this, I'm not guaranteed that I will have energy at 100 and 200 and 300 and 400. But I know I'm not going to have energy at 175 hertz or 225 hertz. So I'm just going to look at multiples of the fundamental frequency, which are the harmonics, Matt. So I say, good, I got it. Energy will only be at the fundamental and the harmonics. Interesting note, not all the harmonics will or may have energy. How did I do on part D? Sean, we're doing good back there? All right. Okay. All right, that's A, B, C, D. Parameter estimation, our last lecture together. This is great, Gaussian parameter estimation. Brings back memories of our fun lecture last Friday. Okay. So it says here, sample size is 77. So n is 77. The standard deviation of the sample is 4.8. the confidence level is to be 90%. The sample mean is 63.7. Determine an estimation on the population mean. Now, the population mean is mu. Do I know mu? No. But the best I can do is estimate it. Okay? So I write down what we have. N is 77. The standard deviation of the sample is 4.8. I want 90% for my confidence level. And the sample mean is 63.7. All of that was given. Now, what do I remember? Ryan, sorry, question? Oh, no, I thought I saw the hand go up. Nope, no problem, no problem. So what do I remember from our exciting lecture on Friday? This formula here. Mu equals x bar plus and minus, and then the z sub alpha over 2 times s over the square root of n. Now, I think I have everything except the z sub alpha over 2. And you know me by now, I like to draw this so I don't make a mistake. So here's our Gaussian curve, and between minus and plus z sub alpha over 2, I want the area to be 0.9. That's because we have a 90% confidence level. Now, since we're using a single-sided table, I'm going to make the area 0.45. I go to the z table. I think we had this exact example in the lecture. Going to the z table, and I look up an area of 0.45, I get 1.645. Ryan, help me out.
If the sample was under 30, you would have to use the student's t, right?
Exactly. If the number of samples was less than 30, we would use the student t. Exactly. Perfect, Ryan. And I'm pretty sure we have an example coming up of the student t. So now I just plug everything in, and I get x bar plus and minus z sub alpha over 2 times the standard deviation divided by the square root of the number of samples, and we did it. And you can report the answer either way. I have or here, so you don't have to worry. As long as you get the right answer, that's good enough for us. That's a basic Gaussian estimation problem. Oh, I thought we were good on that. How do we do it? We're up to F. We're up to part 6. This is good. I wonder what the record is. Okay. Oh, a question.
So when you're finding z alpha over 2,
Yes.
could you also use 0.05 instead of using the 0.45?
You lost me. Let me go back. Help me out.
So for the confidence interval, if it's 90%, right?
Right. The confidence interval is 90%. I'm with you.
Could you use the area under the right tail to find z alpha over 2?
Yes, but our table doesn't have that. No, I like very much what you're saying. You're saying the area from here to here is 0.45.
No.
So the area from the tail, sorry.
No. What you were saying, so that area is 0.45, and the area under the tail is 0.05.
Exactly. The area under this tail is 0.05. You are absolutely right. Now, help me out. The z table I'm going to give you is the one from the book. And the z table from the book only gives us the area from 0 to z. So it's easier to use 0.45. Did I do okay?
Yeah. The table that we were using, at least I was using, had the area under the tail.
Right. Was that in this course?
Yeah.
Was that the student T table?
No. Maybe it was from prop set.
Yeah, because this is the only table we have for the Z in this course. And I know it's different than the prop stats one. So make sure you bring up an excellent point. My colleagues, this table is listed and posted with the exam. Make sure you know how to get the answer using this table, because this is the table that you'll have. So I'm very glad you asked that. So what you need to do is to go to 0.45. Did I get your point okay? And just to round that out, I know it's hard to read on the screen, but my colleagues, you probably have it right with you. This is one of the few cases that we get interpolation for free. This is 0.4495, and look at this. This is 0.4505. So it's right in the middle is 0.45. So that becomes 1.645 is how we got it. You asked a great question. Did I do okay? So bottom line is know how to use this table. 2 questions, Matt, and then Ryan.
Do we have to interpolate on this exam if the value does not fall directly between 2 values?
No. Well, you have to interpolate on this exam if we don't have a value that's exactly between the 2 given values. No. Only use interpolation if you get it for free. Okay, good. Ryan?
That would be my same question. It was just, do we just pick the closest value?
Just pick the closest value, unless it's something obvious like this.
Yeah.
All right, excellent. Fantastic. Okay. I'm trying to hide the answer from you. Ain't I terrible? Okay. Right down here on the bottom. What key mathematical observation, which we mentioned in class, was used in the derivation of the Fourier transform from the Fourier series? I see Justine's eyes focusing like a laser. She's thinking. She's thinking. You might remember we had this periodic signal. Okay. The width here might be T1 of the pulse. And then here is the period capital T. Now, the Fourier series gets us this. We can get the representation of this used in the frequency domain using the Fourier series because it's periodic. So now, what would happen if we had a non-periodic signal? Namely, what would happen if we just had a single pulse? So how do I get this here to look like this? Fantastic. Let capital T approach infinity. So what happens is you let capital T go to infinity, and in this case, our periodic signal becomes non-periodic. So what Fourier could do then is go back to the Fourier series and take the limit of the Fourier series as capital T goes to infinity. And what you then get is the Fourier transform, which is great. That was a very nice way to get from what's called the Fourier series for periodic signals to Fourier transform. What's the Fourier transform? For non-periodic or aperiodic signals. That gets us through F. But wait, there's more. How we doing so far? Good, good. I'm looking around. We're all good. Okay, now, G. 3 important assumptions must be valid for the binomial distribution to be applied in a problem. What are these 3 assumptions? I only asked for 2, but come on, we're here on a Monday night. We're going to bang this out. What are the 3 things? Ryan, give me at least one. Right, we have an independent, so you have a series of n trials. Each trial must be independent. Good. What's another one? That's right. I heard someone say it in the home audience. Each trial must have the same probability. The probabilities cannot change. And Sam, I heard you say this. Sam said that, what'd you say again, Sam? That's right. Sam said that you could only have 2 outputs, pass or fail. Okay? You can't have more than 2 different outputs. Now, did I write all this down? You know I did. You know I did. Any 2 of the following are valid. N trials, each trial is independent. Each trial has only 2 possible outcomes. Third, the probabilities for each trial are constant or the same. Those are the three things that would be used to be the thumbs up to apply the binomial distribution. How we doing? I see smiles. I see joy on people's faces. We're doing it. Okay, that's A, B, C, D, E, F, G. Surely this is the end of it. Oh, no, there's an H. You are given a Gaussian random variable whether you want it or not. Okay, you're given this Gaussian random variable and it has a mean of 23.7 and a standard deviation of 0.79. Determine the probability that the random variable x is less than or equal to 22.1. Dun, 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 dun. Now, I like to write everything down and to draw it out so I can visualize what's happening. You don't have to do this, but I find this really helpful. So I say, okay, first thing I need to do is I need to do the change of variables. Okay, I need to do the change of variables. Now, do I have to memorize this formula? No. This formula is given on the formula sheet. So it's x minus mu over sigma. So I say, excellent. I think we know everything. Mu is 23.7. Sigma is 0.79. Now, what's the value of x? The value of x is given here, 22.1. That's the value of x. So I plug everything, Ryan, into the formula, and what I get is, roughly minus 2.03. Plugging in x minus mu over standard deviation. Okay. Now, I like to draw to make sure I don't make a mistake. So, because surprisingly, I think this is an easy one to make a mistake on, even though you understand it. So it's minus 2.03. So we want to have the probability of x being less than 22.1, which is the same as z being less than minus 2.03. So I draw the Gaussian curve, and here is minus 2.03. I want to get this area here. Now, this gets back to the excellent point we had just a few moments ago. We have to know how to get this using a single-sided table. So I use symmetry. Home audience, we use symmetry here on a Monday night on campus. Symmetry here says this area is the same as that. And that's what I want. Now, can I get that from the z table? Not directly. So I go here, this area from 0 to 2.03. I can get that from the z table. So I go to 2.03. Let me do it once, just so you know we can do it. 2.03. All right. I know it's hard to read at home. 2.00, 2.01, 2, 3. 2.03. If I'm reading it right, it should be 0.4788. So 0.4788, I say, excellent, we got it. Okay. That means, and here we're using the 0.5, that means the area under the right tail is 0.5. Why 0.5? Ryan. That's right. The whole area is 1. And Ryan, you just used symmetry, which says the right half side has an area of a half. So a half minus this area that we just found, which is 0.4788. The area is 0.0212. Area code for Manhattan. Okay. So we then say, excellent. What do we now get? We get the probability, at least for part of Manhattan. All right. That's it. Look at this. We're up to I. This is wonderful. Boy, oh boy. Sean, how can I help? Excellent. Sean is asking a question. And Sean, I'm glad you asked the question. And I heard in your question about a sample mean, and I'm thinking parameter estimation. This was not a parameter estimation problem. This just says I got a Gaussian random variable. Now, I'm telling you it's Gaussian. What's the probability of that Gaussian random variable being less than 22.1? This is not Gaussian parameter estimation. There's no n. There's no sample here. None of that. Did I do okay, Sean? So this is a straightforward Gaussian problem. Oh, this is wonderful. All the happiness we keep going. Problem 1 will never end. Ah. You are given n sensors. Okay. The probability of a sensor working is p. Now, the hardest thing about these problems for me, Justine, is I got to read them very carefully. Okay? The theory is not the problem. It's the reading of the words to make sure I got the right understanding. So here it goes. It says, write an expression for the probability of no more than 2. Now, no more than 2 means, for example, 3 is no good. No more than 2 sensors will not work in a group of n sensors. All right, wait a minute now. No more than 2 will not work. That means 0 cannot work, 1 cannot work, and Bree, 2 cannot work. That's what this is saying here. Bree, do we agree? What do you think? Okay. Use a binomial distribution. You don't have to simplify. Just write the correct basic expression. So I say OK. So the probability of no more than 2 sensors will not work is a probability of 0 not working, Matt, plus the probability of 1 not working, plus the probability of 2 not working. Now, how do I then convert that into mathematical notation using the binomial distribution? The probability of 0 not working, that's n choose 0. Now, be careful. The probability of not working is 1 minus p. P is the probability of working. So this is 1 minus p. How many not working? 0. So if 0 are not working, that means n must be working. So p raised to the n. I thought this was tricky. The next one, n choose 1. 1 not working. What's the probability of not working? 1 minus p. How many not working? 1. That means n minus 1 must be working. That's p raised to the n minus 1. Similarly, for the next term, and you're done. That's it. That's good enough. But I thought that was subtle. Easy to slip up on that. How do we do? Surely, that's the end of it. We don't have a Shirley. Okay. Jay. This is a harder one now. Matt, we're getting this a little harder here now. You once again, whether you like it or not, are given a Gaussian random variable. Mean of 12, standard deviation of 1.8. Determine the probability that we fall between these two numbers. So now we have a Z1 and a Z2. Okay. So Z2, I take the lower value. You can call Z1 the other one. Doesn't matter how you plan it. See, I call this the lower x2 and the higher x1. If you want to do it the other way, it doesn't matter. So what I get is Z2 is x2 minus mu over sigma. Where do I get that? From the formula sheet. By the way, this converts a Gaussian random variable to another Gaussian random variable with 0 mean and a standard deviation of 1, in case that's ever one of these trivia questions. All right? So we say, excellent. So it's 10.8 minus 12. Whoa, where did I get these numbers? Justine, they were given the 10.8 and the 12 and the 1.8. All that's given, I get this. I do the same for Z1. I get this. You know me by now. I got to draw this. I got to draw this. I draw the Gaussian curve, and I want to know the area from minus 0.67 to minus 0.33. That's here. Is this area easily given in our Z table? No. What do I have to use? Symmetry. Okay. So I say that area equals this area. Why? Because of symmetry. Now, from the Z table, I have to look up the Z table twice. So the area between 0 and 0.33, that's this area right here, the area from 0 to 0.33, that's given here, 0.1293. Now, the next thing I do is I look up the area from 0 to 0.67. So I look up all of this area. And the area from 0 to 0.67 is 0.1193. All right, studio audience, what do I now have to do to get the answer? No? That's okay. Here, help me out. I got the area from here to here. And I got the area from here to here. And I got the area from here to here. I want to know the area from here to here. Subtract. Subtract. So what we do is we subtract the two areas. So I get 0.2486 minus 0.1293. So this is the area from 0 to 0.33. Here's the area from 0 to 0.67. I subtract and I get the shaded area, which is what I want, 0.1193. How do we do? Ryan? Ah, you don't like the way I draw my zeros, Ryan. No, I know you. That's why, you see, that's it. So I draw something this. People might say, is that a letter O or the 0? So I don't know. The convention has been, but please help me out. This makes it a 0. Is that not done anymore? That's old-fashioned? Probably, right? Sorry, Ryan. You can tell that I'm out of date here. I thought I was cool, but I'm not. So the 0 with the stroke through it is meant to indicate 0 unambiguously. All right, good. Surely we must be done by now. No, there's a K. All right, we did this in class once, and you had a homework problem on it. I'm sure you can bang this out of the park. See, Bree, none of these problems was meaty enough for 10 points. So 2 points here, 4 points here. You know, it does add up, though. All right, so we have a transient voltage given by this. This equation is valid from 0 to 0.2 seconds. So, Kristen, right away, I know that it is not periodic. Now, define a periodic form of this function from minus 0.2 to 0, which will have only sine terms in the Fourier series expansion. So, my colleagues, if I have a function that's non-periodic, I can do one of two things. Number one, I can use the Fourier transform. Sean, that's not a bad thing to do. Number two, I can cut and paste the signal and make it periodic. And that's what we're doing. But I want to make it periodic so it only has sine functions. Now, is sine an odd or an even function? I have to draw it. Okay? Sine is an odd function. How do I know what an odd function is? F of t equals minus f of minus t. Right? That's what the sine is. Okay? So all you have to do, it looks hard, but it isn't. Take the f of t and set it equal to minus f of minus t. Matt's nodding his head. So Matt, minus f of minus t. Now, it's just you just got to be careful. So you got to, wherever you see t, put in minus t. Right? So So wherever you see t, put in minus t. And then around the whole thing, exactly, Bree, put another minus sign. And then just go through it, and we're all set. Kristen, what do you think? We're okay on this? All right. Is that an L? The problem that never ends. How may I help? Very good. Let me repeat what you just said because you said it perfect. If I had changed this problem and said all we want are cosines, cosine, if I can walk over here, okay? So if this is, for example, t, and this is minus t. Again, by drawing it, I know what you said is 100% correct, okay? So what we get then is f of t equals f of minus t. So this would be an even function. So if I had, as you pointed out, if I had changed the problem to say, okay, I want only cosines, then we'd have to use the even function, and it would be f of t equals f of minus t. Excellent. Great. Did I do okay? Great. Thank you. Perfect. All right. Oh, we're cruising along here. JKL. Oh, this is unbelievable. This is just, You know what gets me scared about this? This is part L. And then I see an indented bullet list. Could there be like multiple parts to the L? It's like, okay. All right. So we say, all right, what do we have here? Ryan, look at this. Who was asking before about the T, the standard, the student T? Ryan, I wouldn't leave you down. I wouldn't disappoint you. All right. All right. So Ryan, yes, you, Ryan, are specifically asked to determine the average lifetime for a whole bunch of new sensors. How many? 5. What's important about 5? Less than 30. Dun, dun, dun. Okay. So it says, for example, okay, everything is done in hundreds of hours, right? Okay. Determine the 95% confidence interval on the mean. So the 95% confidence interval on the mean, we got to use student T because there's only 5. So what do? Let's calculate the average. How do I do that? Add them up, divide by 5. Boom, done. Then you have to calculate the standard deviation of the sample. Okay, so we take each number, subtract the mean, and square it. Okay, so for example, 43.7 minus the mean squared. Matt, the same for the second, the third, the fourth, and the fifth. And Matt, what do I divide by?
Divide by n minus 1.
Good man. How do you know that if you forget it in the panic of a test? It's on the formula sheet. All right, so it's on the formula sheet. You divide by what's called the degrees of freedom. Now notice, what else do I do just to make this really interesting? I add them all up, divide by n minus 1, then I take the square root. So I get a standard deviation of 1.625. All right. All right. Now, wait a minute. What's this alpha stuff? oh, wait a minute, this alpha stuff. What's my confidence interval? Excuse me, my confidence level? 95%. That means the tail of the distribution is 0.05. Oh, I have to draw this. I'm surprised I didn't draw this. By the way, the student t looks a little bit like Gaussian. Okay, and it becomes Gaussian as n approaches infinity. So here, so if it looks like this, and it's supposed to be what was it, 95%? That means the area of the tails is 0.05. And Ryan, help me out. It was 90%, right? So the tails is 0.05. That means one of the tails is 0.025. So with the student t distribution, it's important to get one of the tails. Again, area is 90%. That means the tails is 5. Divided by 2 to get one tail, you get 0.025. So 0.05 becomes 0.025. Now, let's use the student t table. Let's just do this once so you've seen it again. Now, for the student t table, degrees of freedom is n minus 1. So degrees of freedom is 4. So we want 4 at 0.025. Okay. So 0.025 degrees of freedom is 4, 2.776. Okay, 2.776. Excuse me. 2.776. And what we get is our estimate of mu is somewhere between 42.183 and 46.217. How do we do? Now, at this point, oh, sorry, Matt, help me out.
Would you get points off if you didn't put that, like the 42 is like 4200? Because in the beginning it said that it was like each one of those numbers is expressed.
No, you're being too good, Matt. Matt's question is, should I write it as 44.2 is really 44.2 in hundredths? No, you don't have to worry about that.
Okay.
Thank you, Matt. The way I wrote it here is fine. But you're right, these numbers are all in hundredths, but that's okay. We don't need that.
Okay.
Good, Matt. Very observant. All right, good. Now, at this point, I actually had a question that I always kind of like to throw out. I think it's kind of fun. I say, wait a minute. How about an 80% confidence interval on the mean? Now, hold it a second now. Whoops, what did I just do? Oh, I don't know what I did. Okay. Good. I somehow undid it. Okay. Let me ask you a question before we see the answer. That's the interval for 95%. The interval for 80%. It's going to be bigger or smaller? I have a multiple choice. Some are saying bigger, some are saying smaller. Let's take a look. Ryan, let's take a look. So what we have is repeat this process. Get the 80% confidence. My colleagues, all you need to do is look up a different value. And look what we get, 43 to 45. Right? So it's 43 to 45. And this is 42 to 46 for 95%. So 95% says we go from 42 to 46. If you wanted to be only 80% confident, you go from 43 to 45. So what do I notice? The confidence interval for 90%, or excuse me, 95%, goes from 42 to 46, and it's bigger than the confidence interval for 80%, which is 43 to 45. Matt, how can I remember this? My simple little thing in life. I used this in class. Forgive me for repeating, home audience. Someone were to ask you what's going to be your GPA at the end of this semester, for this semester, and you must be 100% right. It's 2 plus or minus 2. And if they were to say, okay, you don't have to be 100% right, just give me a ballpark. You might say, okay, 3.1 plus or minus 0.2. Okay? If you tell me I have to be absolutely certain my life depends upon knowing the high temperature in Hoboken tomorrow, I'm going to say the high temperature is going to be between minus 200 and plus 200. We're either going to freeze or we're going to burn up. Doesn't matter then. Right? Somewhere in that range is going to be the high. But if you just kind of want to know, should I wear a coat or a sweater? What's the high temperature going to be? I say, I guess around 52, 58, 54, 53. Who knows? There's a big difference. The more accurate you got to be, you want more margin. I thought this was a fun problem. At least I did. I don't know if the majority of people had that same insight. Oh, and this is the one they really love. This is it. We finish it off with a bang. Discuss the result. Oh, did I hear pain? I see suffering in people's eyes. They have to write a full, complete sentence. I know you can do this. You all got 800 on your SATs, verbal and so on. I know you can do this. So all you have to do now is just discuss it. So I say, look, the higher the confidence interval, the greater the confidence level. The higher the confidence level, the greater the confidence interval. So if you need to be 100% certain, you're going to make it the biggest possible interval you can to make sure you fall inside that. So the higher the confidence level, the greater the confidence interval. I thought that's nice to know. Kristen seems to agree. Good. All right, is that it? Yes. Whew. Hallelujah. We're now on to question 2. The rest of the exam is downhill, boy. We did it. We went through A, B, was it up to L? Huh? And L had 2 parts. 3. Ooh, sorry. All right. Bree, we're now looking at this. Oh, yes, my colleagues, for those of you who attended Friday's lecture, and if you didn't, I want you to know out there, I'm not going to mention names, but there were people in normal seats I didn't see on Friday. In particular in Burchard 118, back in right field. I'm not going to mention names, but there were people there that weren't there. I saw them, but they weren't there. I mean, I saw them virtually. So my colleagues, I'm worried about you. You got to keep showing up to class. So for those of you who were in class, and again, shame on you if you weren't, I mentioned that I sometimes ask the parameter estimation problems, Bree and Kristen, backwards, right? Just to throw a curveball because it's baseball season. We have opening day coming up this week. So we say, excellent, we're going to do that. A colleague, who, I don't know, a colleague says, I've used Gaussian estimation. And I tell you, I think the mean is bounded by 37.2615 and 38.5385. And I say to him, how confident are you? 88%. And the standard deviation was 3.1, and then they walk away. And Matt, I say, wait a minute. I never asked my colleague, what was the sample size? Oh, well, can I work backwards and determine the sample size? I think I can. I think I can. Okay. Now, my colleagues, this is where some people get stuck, which means they can't do anything else after this. I don't want you to get stuck on this. Okay? I don't want you to get stuck on this. What's the formula? Mu equals x bar plus and minus something, right? So, Justine, I have mu greater than or equal to, less than or equal to these 2 numbers. What's x bar? How do I get x bar? Right, x bar is right in the middle. You see? Bree, as you know, mu is x bar plus and minus something. Find the middle point. That's x bar. That's trick number 1. Well, how are we doing? Okay, so now I get x bar is 37.9. Now I say, well, wait a minute then. I can then write that mu is 37.9 plus and minus something. I then figure out what that is by subtracting, for example, 37.9 from 38.5385. And what do I get? 0.6385. What do I now know? This whole quantity is equal to 0.6385. I got it. How am I doing? Good. My colleague in the back, left field, how we doing? Good? All right, good. I say, excellent, we got this. So now I know that 0.6385 equals z sub alpha over 2 times s over the square root of n. What's the unknown? N. But first, Kristen, I have to be very careful. And I have to determine z sub alpha over 2. And what do I know, Sean? Sean, you and I know this. We know that our confidence level is 0.88. Justine, that was given. That means this area to the right is 0.44. So I go to the z table and I say I 1.44. Let's do this. I think, was this the other case where we get interpolation for free? This is so exciting for me. 0.44. Yes, look at this. This is the second case where I've encountered we got interpolation for free. Where am I here? I don't know. 0.4394. 0.4406. Look at that. All right. So now we can say, okay, it's 1.5. 1.555. Okay. Not bad, Ryan. We got it too. We got this here. So we then get z to be 1.555. I solve for the square root of n. We get 56.998. So due to slight round off error, n is 57. So I asked you this backwards. How did we do? Devin, how are you out there? All right. Okay, good. All right. Mr. Kapasig, I'm not forgetting you, John. Yes, Matt?
Always round up then, right?
Yeah, I mean, I wouldn't have taken off points. Let's say if it was 56.2. If someone said 56 or someone said 57, it's just rounding off. I wouldn't have taken off errors, points. So think of it as 56, and then you can go up to 57 or back to 56. So, all right. I'm disappointed. Was that all a problem too? Oh, what a letdown. I mean, we just went through like up to L or something. Oh. Sean. Oh, this is a hard one. This is a little tricky. So for those of you at home, you might want to pause the recording, get a glass of soda or health. And you're also healthy. You don't drink soda. You could have some water, do a little stretching. We'll come back and we'll do this. Okay. So here we go. This is a bit tricky. It's subtle. But you're well able to handle this. All right. All right. Once again, whether you like it or not, you're given a Gaussian random variable. And the mean of the Gaussian random variable is 7.3. And the standard deviation is 1.57. So Ryan, here's the trick. We're told that the probability that that Gaussian random variable is between two numbers is 0.1907. Problem is, we're not told the second number, the upper bound. Dun, dun, dun. Okay, so this is now asking it backwards. So I'll go as far as I can until I get stuck. Z1, I got that. That's using 4.47. So Sean, I get minus 1.80. Now, this is the subtle part. I expect questions here. This is very subtle. What's the area from minus 1.8 to 0? Now, in a moment, I'll tell you why I'm asking that. Okay? But the lower number on the z-axis is minus 1.8. So, Matt, the area from minus 1.8 to 0 is the same as the area from 0 to 1.8. So I look this up, and I get 0.4641. That's bigger than 0.1907. That means x2, the unknown, is less than 0. Exactly right, Ryan. Let me say it again. The area from minus 1.8 to 0 is 0.4641. Notice the area from minus 1.80 on the z-axis to an unknown number, 0.1907, that's smaller. So therefore, that upper number is somewhere here. It's very subtle. Justine, how did I do? Did I do okay? Very subtle, I think. Okay. How am I doing? Am I doing okay? Doing good. I see a question. I see it in your eyes. I see the question mark. Can I be of any help or no?
So the 1.8 is the z-value, so then you got the 0.46.
Perfect. Exactly right. I got the z-value from here, right, by taking the number, subtracting the mean, dividing by the standard deviation, minus 1.8. As you point out, that is symmetric, so I got the area from 0 to 1.8 from the z table. And that's 0.4641. So that means I know this area here, from minus 1.8 to 0, is 0.4641. How did I do? Now, the area between these two numbers is less than that. That means the upper number must be less than 0 because the area from here to 0 is bigger than what I'm given. How did I do? All right. So, Bree, I see a thoughtful look. Am I doing okay? All right. Anyone else? I welcome questions. So, z must also be negative. Thus, we have minus 1.8 up to minus z2. And Sean, this equals, by symmetry, z2 to 1.80. Now I got it. So, once again, the 0 with the stroke through it. Okay. The area between 0 and 1.80 is 0.4641. The area between 0 and z2 is the area between 0 and 1.8 minus 0.1907. Does that make sense? Right? I know that this area here is given as 0.1907. So the area from 0 to 1.80 minus 0.1907 is the area between 0 and z2, which is 0.2734. From the z table, z2 is 0.75. Kristen, we got to be careful. If I now go back to solve for x2, do not use 0.75. It's negative 0.75. You then use negative 0.75, and you get the value of x2 to be 6.12. I thought this was like a maze. You had to go through a couple of different steps. I thought it was good. What do you think? I see a smile. I love it. I love it. Anything I can help with on this? We're doing good. There's 6 questions. This is question 3. We're halfway through. Okay. Ah. Oh, great, great. I love this. My colleagues, let me, here. Here, tell you what. Let me draw something. I don't want you to get lost in the problem first. I know you know this, but I want it to be at they say, your fingertips. Here. Sensor working is P. Here are 2 sensors in series. Each has a probability of P working. What's the probability that this system works? Now, for the system to work, Bree, both sensors have to work. So what is it? How does this system work? Sensor 1 has to work, and sensor 2 has to work. In the problem, I say we can assume independence. If we assume independence, what do? Matthew?
1 minus the probability of sensor 1 failing.
Oh, you're making it too complicated. You're giving me the right answer to my next question. So I'll come back to you. My colleagues, you got the more difficult answer. This here, the probability of this working is P. Probability of this working is P. The probability of both working, P squared. That's it. Right? Now, the more complicated case, which I should have done first because Matthew was already ahead of me here. Okay? We now have 2 sensors in parallel. Sensor 1, sensor 2, each working with a probability of P. Now, there's one way to solve it, but I wouldn't recommend this. When will this system work? When sensors 1 and sensor 2 work. When sensor 1 works and sensor 2 doesn't. When sensor 2 works and sensor 1 doesn't. That's 3 different cases. You could figure it out and add them up. Don't do that because I might give you 5 sensors. If I give you 5 sensors, I'm going to drive you crazy. So here's what you do. If you can't figure out the probability of it working, what do you figure out? Good man. Take me through it. What is the probability of the upper path not working? Probability of the upper path not working, 1 minus P. What's the probability of the lower path not working? 1 minus P. When and only when does this not work? When the upper path and the lower path do not work. So the probability of this not working is 1 minus P squared. What's the probability of it working? Probability of it working is 1 minus that. I love this. Now that's easy. If I had 5 sensors, just replace the 2 with the 5. Okay. Again, probability of the upper path not working, 1 minus P. Lower path not working, 1 minus P. The system not working, both paths not working, 1 minus P squared. Why? Because they're independent. That's the probability of not working. What is the probability of working? 1 minus that. That's what I wrote here, just as a warm-up. Just to, you're out in the bullpen warming up, all right? Just to get the muscles flexing. So we got it. Probability of the system working is 1 minus P squared. Okay, now, my colleagues, I give you a crazy-looking mess of sensors, okay? And I ask you to give me the answer. So let's look, Justine, at the crazy mess. What problem is this? 4. Just We're coming to an end. We really are. We really are, Justine. I got to rotate this. View. I want to rotate this clockwise, I think. Oh, man, look what he's doing to us. You know, it's Christmas, it's Passover, spring, it's baseball season. This guy's driving us crazy, man. This is it. All right. So we have 1, 2, and then 3, 4, 5, right? All right. I'll draw the 1 on the bottom in a moment. 6, then 7, 8, 9, 10. Okay. I don't think it's that bad. Okay. What's the probability of this working? 1 minus the quantity 1 minus p cubed, right? What's the probability of 1 and 2 working? P and P. What's the probability of the whole upper path working? P times P, that whole quantity times 1 minus the quantity 1 minus P squared. I have all this written down. Kristen, am I doing okay? Likewise, Justine, on the bottom. I have what? 7, 8, 9, 10. So that's 1 minus the quantity 1 minus P to the 4th. Times P. So with that in mind, let me get the view back to, whoops, what did I do? View back to counterclockwise. Sorry, Ryan, I think you were still copying. You'll get it, Ryan. I can't believe I gave this exam. I am a mean professor. I have a streak of meanness in me, I think. I don't know. I have to examine this after our exam, too. All right. So the upper path, probability upper path working is P times times 1 minus the quantity 1 minus P cubed. And the lower path working is very similar. Now, the probability of the system not working is 1 minus this quantity, right, times 1 minus that quantity. That's the probability of the system not working. What's the probability of the system working? 1 minus the probability of the system not working. Notice you got to go back and forth, right? You got to, Justine, this is good. You got to keep like moving around here. It's good. Now, we substitute in P equal 0.99 because I gave you that. And if you calculated it correctly, or maybe if I calculated it correctly, you get 0.9998. Four down, only 2 to go. We're coming down the home stretch. Oh, help me out. Sorry? Yeah, if I go back up, hold it a second. Right, so you're here. Sorry, I'm not following. It's my fault. So you're looking at P times P, 10 times 1 minus P cubed.
For that first part, why didn't you do the probability of not working for those two?
Right, I had to do, excellent question. The question is, why did I not calculate the probability of these not working? By the way, this quantity in square brackets is the probability of working. Well, it is the same. Help me out, and it's my bad for not explaining it more clearly. What's in the square brackets is the probability of it working. So P is also the probability of it working. And P is the other probability of that other sensor working. So this whole term is the probability of all those sensors in the upper path working. Awa, help me out. I don't know if I'm doing a good job here. So Awa, what I found out was the probability of sensors 1, 2, 3, 4, and 5, all in that whole group, 1, 2, and then sensors 3, 4, and 5, all working. So the trick is, just as I did here, Awa, I must first get the probability of the path working. Okay? So the path working is P times P times the probability of this working, which is 1 minus the quantity 1 minus P cubed. So now I have working, 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 and I multiply them together. That's similar to what I had over here with P. Now I then say, what's the probability of that not working? 1 minus P. So I only get 1 minus the entire quantity of the upper path working. Am I doing okay? Awa, help me out. Did I get it? So what I do first is I have to calculate the probability of the entire path working. And then I take 1 minus that. No, because could I have done P times P cubed? No. P cubed will not capture all the ways that the system will work. Awa, I could have just sensor 3 working and 4 and 5 could fail. I could have all 3 working, or sensor 4 working, 3 and 5 not working. Sensor 5 working, 3 and 4 not working. 3 and 5 working and 4 failing. There's a lot of different combinations. So it's not just P times P cubed, because I have to take into account if things are in parallel, only 1 out of n has to work. Awa, did I do okay? You sure? All right, good. All right, my colleagues. Oh, my legs are getting stiff. My goodness. All right, now, view. All right. Oh, what did I do? Caroline, I don't know my clockwise or my counterclockwise. All right. I think we should be back. All right, so that's it. I think we're done with problem 4. What do you think? I hear a standing ovation. Okay. All right. I guess it must have been around Thanksgiving or something. I felt generous. For this one here, you didn't have to, you got full credit if you just set it up right. It's a binomial distribution, okay? Now, binomial, I mean, I got to read them real slow because there's, we could wind up tricking ourselves here. So you got 10 sensors. The probability of a sensor working is 0.98. Determine the probability there's no more than 3 non-working sensors. So the probability of no more than 3 non-working sensors means the probability of 0 not working, or 1, or 2, or 3. And just like we did earlier tonight in that multi-part question, we get this here. Okay. I'll get to the bottom note in just a moment. Are we okay on this, my colleagues? Now, we have close to, I think it's around 330 colleagues in the sum total of sections A, B, and C. So I know out there somewhere, here, out there in the archive land, there are some people who see this problem differently. They say no more than 3 non-working sensors means there's at least 7 or 8 or 9 or 10 sensors working. Okay. Now, some of you may not see this. That's okay. But when we say no more than 3 non-working sensors, that's the same as saying if I have 10 sensors, I got 7 or 8 or 9 or 10 working. So you got full credit either way. How do we do? thoughtful crowd here tonight, very thoughtful audience. You select, again, 10 sensors. The probability of a sensor working is 0.98. Determine the probability at least 2 sensors fail. Now, at least 2 sensors fail. Okay, so wait a minute now. At least 2, right? That means 2 or 3 or 4 fail, right? That's equal to 1 minus the quantity, the probability of 0 or the probability of 1 fail. Let me pause. Do you see that? This also equals, can someone help me out? 1 minus this and 10 choose 10, 10 choose 9. This is the probability of 10 working. This is the probability of 9 working. Help me out. How can I argue that? At least 2 fail. Kristen.
So in that case, either 0 fail or 1 fail, so then you want 1 minus that because that's not what you're
Perfect, exactly. Kristen, thank you. Great. All right. Wonderful. Huh. Well, all good things must come to an end. What problem are we now up to? We have our last problem. I just heard a round of applause from the home audience. All right. Okay. All right. Now, I think this is a chapter 4 question, and I think I said in our lecture, I'm running out of ways to ask this question, so I don't know. I mean, I have to have I don't know. I just got to think about this more. So, but I think, as they say in baseball, this is right over the plate. There's nothing fancy here. You should get this. All right? So, you got a sensor that has an analog signal, maximum output frequency, F max. Tell you what, since this is the last problem, Sean, we should do some animation on these. You know, have the figures overdrawn here. We can get fancy on this stuff. All right. We also need to add music, I think, but that's just me. All right. So we have a sensor. And the output of the sensor is F max. You're connected to a low-pass filter. If you don't mind, I'm just going to put in the acronym, low-pass filter. And the low-pass filter has a cutoff frequency of F sub C. The output of the low-pass filter is connected to an A to D converter, N bits. That means each sample is converted to N bits. The converter samples at a rate of n times the minimum required. Oh, that sounds tricky. We got to come back to that, Bree. All right. What is the purpose of the low-pass filter in the system? Please be specific. I hope you don't have to memorize this. I hope you can put it in your own words. It's to make sure that we get rid of the unwanted noise high-frequency signal. Another way of saying it is, it helps me to know the highest frequency coming into the A to D converter, which means I can then know how to sample. So however you want to say it, but you remove the high frequency noise, or you can have a better understanding of the highest frequency coming into the A to D converter. Now, how would you determine or select the corner frequency? Simple. I would make FC equal F max. But look at this. I say, my colleagues, there's a simple answer. But I would take it as a personal favor if you would discuss why you might want to select something different than the simple answer. So if the simple answer is to set FC equal to F max, what's the slightly more complicated answer? Just a little bit higher. Because by the time you get to the corner, you're already dropping off. So we'd like, but I want to make sure, right, I don't make it too high. Because then I'm getting close to the unwanted signal, perhaps. So more insight. may want to select f sub c to be slightly greater than f max, since the low-pass filter is already attenuating the signal at f equal to fc. What's the advantage of increasing n? More bits per sample. A number of different ways of saying it. There's less resolution error. I should say greater resolution. I don't know if well, I didn't say it very clearly. I get less error if I have more bits. I get more accuracy, greater resolution. And what's the advantage of decreasing n? Less bits to store. Are we going up to L on this one too? Man, this guy crazy. What was this guy thinking with this exam? I don't know. Kristen, this guy's out of here. A, B, C, D. I don't know how many more we're going to go. All right. Are we good? Coming down the home stretch. This was an unfair question. The answer was no impact. Question is, as the sampling rate is increased, what's the impact on the resolution error? Remember, what's the resolution error? You have a ruler, and a sample comes here. Ryan, help me out. A sample is here. Which level do I pick? Exactly, the closest level. So I pick and I say, this is the height of the sample. The difference is the error. Now, that's called the resolution error. If I sample faster, does that have any impact on the resolution? No, Bree's shaking her head no before I even finish the question. Exactly right. Has no impact. I put a smiley face in so they wouldn't beat me up. Oh. This is it. Determine an expression for the amount of storage needed for 1 hour worth of measurements. Okay? So in this case, I said, Ryan, I let f sub c equal f max. All right, now, follow the units. The units will give you the answer. So here's what happens. Here, let me cover M. If I tell you the highest frequency coming into the A to D converter is f max, how many samples do you need to take? 2 times f max. But I mentioned in the problem, we oversample. So M is like 1.25 or 1.5. So I don't sample 2 times f max. I sample 2 times m f max. What are the units? Samples per second. Exactly. Tell you what. Suppose f max was 1500 hertz. Forget the m. Ryan, what would be the minimum number of samples per second? Fantastic, Ryan. You nailed it. The minimum number of samples per second is then 3,000 samples per second. Now, that's living on the edge. There's no margin for error. So if I were to tell you we oversample by a factor of 1.5, that's what I call M. Yeah. So instead of sampling at 1,500 times 2, that's the minimum. I oversample by a factor of 1.5. So it's 2 times f max times 1.5. Ryan, did I get it?
I was just confused.
Yeah, the wording perhaps wasn't clear. I apologize. But we're good now?
Yeah.
Now, that's samples per bit. N bits per sample. Oh, good. The samples cancel. I'm left with bits per second. I then multiply that by 60, because there's 60 seconds in a minute. and I multiply by 60 because there's 60 minutes in an hour. Look, the minutes cancel, the seconds cancel, the samples cancel. I'm left with bits per hour. Bits per hour, I got it. That is the answer. Okay, just a note there. And look at this. I hate to disappoint you. The end. We're done. How do we do? What other way to spend a Monday night, right? I mean, this is great. Right? Once again, Sean, Jesse, Matt, the whole gang, thank you. I really appreciate it. Signing off from Pierce 116. Thanks, everybody. Well, was it worth your while? Good. You're very welcome. It's my pleasure.